Up next in our derivative shortcuts is the chain rule, and the chain rule also applies the use of the power rule, but in a little bit different way. So the chain rule is used when you have a compound function. Basically, it's a function within another function. And so if you look at the problems below, I've got a polynomial raised to a power. So the inner function, in this case the h function, is that polynomial, but the g function is the fact that it's raised to the fifth power. So to do a derivative applying the chain rule, what we do is we take the derivative of the outer, but we leave the inner alone, and then multiply it by the derivative of the inner. And it's a little bit complicated to kind of understand when I write it. It's usually a little bit easier when you look at it in action. I'd love to say I have a little shortcut that I say with this one, you know, like the Lodi high, or the firsty second, but I don't. You just kind of jump in and do it. It's, again, I do the derivative of the outer, and the outer function is, so my g function is the fact that I'm raising something to the fifth power. And so if I'm doing the derivative of that, g prime of x, I would do 5x to the fourth. Except for it's not x, it's something else that's raised to the fifth power. So I do the 5, not x, something else raised to the fourth power. And that something else is what's inside of there. So 5x cubed plus 6x plus 4. But then I'll multiply it by the derivative of that inside. So the derivative of that inside would be a power rule on that. 15x squared plus 6. We didn't see anything like this yesterday, and so I want to talk about that just briefly. So that's 6x to the first power, and if that's my function, y equals 6x to the first power, then y prime, the derivative of that would be 1 times 6, x to the 1 minus 1 power, or 6x to the 0 power, which is just 6. Okay, so that's how that 6x becomes just 6 there. But then again, just like yesterday, no need to simplify, just leave it in that form. It's much easier for me to correct it that way, so I beg of you, don't simplify. You don't hear that often, right? So my next one here, dy dx, because it's a y function. Notice I wrote up here as y prime. That's been done as well. Instead of writing f prime or dy dx, you can write y prime. But I'm going to go with dy dx here. So it's my outer function is that thing raised to the negative fourth power. So I bring the negative 4 down front, and I lower the power 1. Remember, when you lower a negative, negative 4 minus 1 is negative 5. But I leave the inner as is, and then I'll multiply it by the derivative of the inside, and the derivative of the inside would just be 8x, because 2 times 4, x to the first, and then that minus 3 zeroes out. So there is my final answer there. Again, the derivative of the outer is that power on the outside, inner stays as is, times the derivative of the inner. Let's see that in action again. Ooh, what happened here in problem number 3? Well, don't be afraid of that. Not a big deal. We can rewrite that. Remember, a cube root is just like taking a function and raising it to the 1/3 power. And once I have that 1/3 power, we'll see this kind of a lot when we do some square roots, but I have that 1/3 power. Now I can do my derivative. F prime of x is the derivative of the outer. That's the 1/3 lower the power 1, 1/3 minus 1, negative 2/3. Leave the inner as is, and then multiply it by the derivative of the inside. And there's my final answer. One last problem with on this side of the notes. Same kind of thing. Got a rational power. dy dx is, bring that power down front, lower the power 1. I did 1/4 minus 1. Leave the inner as is, times the derivative of the inside. So that is negative 20x cubed minus 4x minus 1. Again, looking at that, that's negative 1x to the first. If that is my y, then my y prime is 1 times negative 1 x to the 1 minus 1, or negative 1 x to the 0, or negative 1, and that's how that end term becomes negative 1. All right, so that's the chain rule. Final answer. Again, leave it in the unsimplified form. We're going to move on to a review of trig, or we're going to talk a little bit about trig. I do derivatives of sine and cosine only. When you get into calc, you'll be doing derivatives of tangent and secant and cosecant and cotangent and all those other things that we talked about. But we start with just the derivative of sine and cosine. And to find the derivative, what I like to do is start by sketching a graph of sine. So if you remember correctly, this is just one period of sine. And what I want to do is I want to use that concept of what a derivative is. And a derivative is the slope of the tangent lines at a given point. And so if I approximate the slope of this tangent line, I might say that slope looks like it's about 1. Now, you might say, nah, I don't know, it looks more like, I don't know, 2. Whatever you want. I'm just going to approximate it as 1 because that's what it looks. It's positive, and it's kind of going up. It looks like almost a 45-degree angle, so I'd approximate that as 1. Then I'm going to approximate the slope here as 0. And I'll do another spot here. I'm just picking spots where it's kind of, you know, just important points on the sine graph, you know, where it changes direction, where it starts, where it changes directions, where it crosses the axis. So you could pick your slopes anywhere you want, but it starts off like 1, 0, then that looks like maybe negative 1. And I'll check my slope here. That looks like 0 again. And then I'll check my last slope here. Maybe that is 1 as well. And then what I'm going to do is I'm going to take all those slopes and I'm going to graph them. Well, it started off with a slope of 1, and then I had a slope of 0, then I had a slope of negative 1, then I went back to a slope of 0, and then a slope of positive 1. And if I connect these, you should see I just created a different trig graph. In fact, what I graphed here was cosine. And so the derivative, if my original function is sine, then the derivative is cosine. So the derivative of sine is cosine. Let's do the same thing for cosine. And some of you might be thinking ahead, oh, I bet I know what it is. I bet it's fill in the blank. Well, let's graph it and see. We're going to go through that same process. So here's my cosine graph. Again, I'm just sketching it here. And I'm going to find all the little slopes on it. So I'll start here at this spot where it starts. That looks like a slope of 0. And maybe here, that looks like a slope of maybe, I don't know, negative 1. Again, I'm just approximating. Next, I have another slope of 0. Here, maybe a slope of 1. And then when I stop, a flat, you know, because remember this curves back down, I have another slope of 0. And so again, I'm going to go through and I'm going to plot all my slopes. It starts at 0, then goes to -1, and then 0, and +1, and then back to 0. And if I sketch that, it kind of looks like a sine graph, except for it's flipped. In fact, this graph is the opposite of sine, because instead of starting up at +1, it goes down to -1. So if y is cosine x, then dy dx, or its derivative, is the opposite of sine. Well, why do we learn this on the chain rule? Because when I deal with sine and cosine, I actually do have two functions, the function of cosine or sine, and then the angle is another function. So the outer function is the trig part of it, the inner function is the angle that I have. And as long as the angle is x, I'm going to be multiplying by the derivative of x, which is 1, so it's not going to change that. But when I change the angle to a different value, like in this case 5x, well, now my derivative's not the same. So if y is sine x, then remember the chain rule, it says the derivative is the derivative of the outer, so the derivative of sine is cosine, but I leave the angle as is, and then I multiply by the derivative of the angle. I do a little bit of simplifying on these because I don't like that 5 hanging out in the end. So I'll bring that to the front, and I will always write it where I bring that product of the angle in over out to the front, because that's kind of a more natural place for it. So there is my derivative applying the chain rule. Again, if I have cosine, I would do my derivative f prime of x by taking the derivative of cosine, which is negative sine, but I leave the inner as is, times the derivative of the inner, and then when I rewrite that, f prime of x is negative 15x to the 4th. The negative will go way out in front. This derivative of the angle will kind of scooch in between, and then the sine of the original angle that I have. So again, I'm doing the chain rule, just applying it to trig. You might want to pause the video and see if you can do 7 and 8, but I'm just going to jump right in and have at it. F prime of x. I've got the sine, derivative of sine is cosine, angle as is. That's the inner as is, derivative of the angle. So I rewrite that as 8x cubed times the cosine of 2x to the 4th, f prime of x. Final answer on that one. I forgot to bubble my last one. Final answer on that guy. And then one last problem that we have, one last cosine. So y is cosine x to the 5th, dy dx is the derivative of cosine, negative sine, angle as is, times the derivative of the angle. Rewrite. Again, this is the only type I rewrite. I'm going to scooch that in between the negative and the sine. Oops. And leave my angle on the end. Final answer. So on today's homework, you should be doing 10-2, evens or odds, applying the chain rule. As always, contact me if you have any questions.